In the previous class, we actually tried understanding image in spatial domain. In fact, we discussed various nomenclature that we use in image processing. We also tried understanding relationship between pixels and also how we can do connected component analysis. Okay, in this class, let us try to understand images in transform domain. Is the slide visible?
Yes, sir.
Okay. So we are going to discuss about image transforms. Um, in fact, you have already learned various transforms. For example, Fourier transform you have studied in signals and systems. You have studied Laplace transforms, I think, in network analysis. You have studied Z transforms also in signals and systems. So as you can see, these transforms are actually taking the signal from one domain to other domain. Okay, so you are allowing the signal to go from one domain to the other domain. So what is special about image transforms? Image transforms also does the same thing. It allows to shift the image in the spatial domain to the image in the transform domain. Um, In fact, this transform domain depends on what type of image transform I am going to use. If you use Fourier transform here, this domain will be frequency domain. I think this you have studied in your DSP course also. A signal in time domain is represented in frequency domain by using Fourier transform. So there are different categories of image transforms, and as I said, all of these are taking the image from the spatial domain to the transform domain. And what is the advantage? Advantage is it helps in performing some tasks easily. I think one of the tasks that probably you would have uh, okay, you would have some difficulty is convolution. So when I do convolution in time domain, so you need to do some operations like you have to flip the signal, you have to shift the signal and find out the common area or the overlapping area and try to find sum of that area. Okay, from minus infinity to plus infinity, I need to complete this task. This is about one dimension. And obviously, two dimension means the flipping should happen both in the x and also in the y direction. So what happens is the operation becomes little cumbersome or difficult in spatial domain. So if I take the signal or the image from the spatial domain to the transform domain, all of you know that I think this is one of the property of Fourier transform also. Convolution in time domain is what is it in the frequency domain? Can somebody tell me?
Multiplication.
Yes. So convolution is a difficult or a tedious task, but multiplication, as all of you know, will be simpler compared to convolution. So what we do is whenever it is difficult to do convolution in time domain, take the signal to the frequency domain, perform this operation, and maybe when you go back to the time domain by doing inverse Fourier transform. So that is one of the advantage of any transform for that matter. It helps in performing some tasks easily. In fact, there are many other advantages. Fast computation of convolution and correlation is possible because there are tools that can perform these transforms very fast. For example, DFT, there is a fast way of implementing it, all of you know, which you have studied in the course DSP, that is FFT, fast Fourier transform. So by using some structure of the signal, I can do fast computation of these operations like convolution and correlation. So the first reason why transforms are useful is you can perform some tasks easily. Good example is convolution. Fast computation of these operations like convolution and correlation is possible. And other thing is the data can be represented in compact form. What do I mean by that? For example, a sinusoidal signal. If I need to represent this data, all of you know I have to sample this signal and store each and every, in fact, each and every sample by using some number of bits for representing each level. Okay. Now, what is Fourier transform of a sinusoidal signal? Can somebody tell me? What is Fourier transform of a sinusoidal signal? If I take Fourier transform of a sine wave, what do I get in frequency domain? One dimension I'm talking about, which I have already done in third semester only. Anybody? How do you represent Fourier transform of a sinusoidal signal or a cos signal?
So in exponential form.
Pardon, please repeat.
Exponential form.
I think your voice is not clear.
In exponential form.
No, no, it's not exponential. Anybody?
Impulse.
Yes, yes. Who is it?
Tarun, sir.
Tarun, correct. So, is a sinusoidal signal will be two impulses in the frequency domain, one in the positive frequency position and one in the negative frequency position. I think all of you know about it. So, when I take the signal, a time domain signal into frequency domain, what I need to store now is only these coefficients. So, for a complete sinusoidal signal, it is enough I store this by using only two impulses, sorry, two values. That is, what is the frequency at which this impulse is existing. That is what we meant by the data can be represented in compact form. In fact, there are many transforms that we are going to discuss in this course, and we'll also discuss about how compact the data can be represented. Based on that, we will also okay, use this for doing image compression. Okay, yeah. So there are different types of image transforms. We have categorized them based on the what is known as the basis function. So I think I need to explain a little about this basis function. Let me go to my OneNote. Okay, I hope the OneNote screen is visible.
Yes, sir.
Yeah. Okay. So what I'll do is I'll just take an example of uh, Fourier transform itself because all of you have. So I'll just write an equation for 1D DFT. Okay, can somebody tell me what is the equation for 1D DFT which you have done in the last semester? Quick. What is the formula for DFT? Summation n is equal to 0 to n minus 1 x of n e to the power of minus ga 2 pi kn by capital M. Is that correct? Hello?
Yes.
Am I? Okay. Then what is the inverse Fourier transform x of n? If you want, you can use a notation x of k like this. It's okay. What is inverse Fourier transform? 1 by n summation k is equal to 0 to n minus 1 x of k e to the power of plus j 2 pi kn by capital N. So notice here, of course, 1 by n is a scale factor. You don't need to worry much about it. This is just a scale factor. This x of k, actually what you are trying to do is x of n is your time domain signal. This is a time domain signal. And x of k, we call it as the Fourier coefficient. At every value of k, its value will be different. These are the Fourier coefficients. Okay, so it's just a constant. At in fact, at every value of k, it will be varying, of course. Now this exponential function, this is actually called as a basis function. Okay, this is a nomenclature that is used. Okay, so what you should notice is any arbitrary signal x of n can be represented in terms of these basis functions. Okay, and depending on the value of k and n, the basis function will take a different shape, and each of this basis function is multiplied with the respective frequency coefficient or the Fourier coefficient x of k. So this is called the basis function. For every value of n, for every value of k, this basis function is going to change. So for each value of n equal to 0 and k, say for example k is equal to 0, if both of them are 0, then the basis function is e to the power of j0, it is equal to 1. Suppose if n is equal to 0 and k is equal to 1, you can see that it is again 1. If both are 1, say n is equal to 1 and k is equal to 1, then it will be e to the power of j 2 pi by n. Assume that I am going for maybe a 4-point DFT, that means n is equal to 4. If that is the case, this will be e to the power of j 2 pi by 4, which is e to the power of j pi by 2. Okay, so this will be the basis function. So for each value of n and k, you will have a specific basis function which is multiplied with the corresponding coefficient to get the representation for a signal. That is exactly what I just talked about, the basis functions. And the speciality of these basis functions is, all of you know about it, e to the power of j 2 pi kn by n, they are orthogonal to each other for different values of k and n. Okay, so I will not go beyond this. I think this concept is already introduced long back. So what we want to understand is, depending on what basis function I am going to use, okay, depending on what is it I am going to use, we classify the image transforms into different categories. The first category, it uses sinusoidal basis functions. In fact, here e to the power of j, all of you know that e to the power of j something, okay, j theta or whatever it is, this can be called as a sinusoidal signal. Only difference is this is a complex sinusoid. I think this concept is introduced earlier in signals and systems. This is a complex sinusoid. Why we call it as complex sinusoid? All of you know, if I just plot this e power j theta, it will be a rotating vector with an angle theta. So this is the real axis, this is the imaginary axis. So depending on the value of theta, it rotates. So it makes one circle and comes back. So as you can see, again it is repeating. So this is a periodic signal, and the magnitude of course changes. So this is a complex sinusoid. E power j something is a complex sinusoid. So if I use this type of basis function, that means a sinusoid, it can be a real sinusoid or it can be a complex sinusoid. In fact, the Fourier transform, it is a complex sinusoid. Later you will see we'll also use real sinusoids. Okay, so if it is sinusoidal functions are used, then we have some transforms. So the examples are discrete Fourier transform, which we have already discussed in the earlier classes also. And the other one which we are going to introduce in this course is discrete cosine transform. There is also one more called discrete sine transform. But we are not discussing anything about discrete sine transform in this course. That is why I have given it in a different color. So we are going to discuss these two, DFT and DCT. Okay. So if I use sinusoidal orthogonal basis functions, this is the category, and there are two examples that we are going to study. If I don't use sinusoidal orthogonal basis functions, I use non-sinusoidal basis functions. Okay, then that is a different category. There are many under that called Hadamard transform, Haar transform, Walsh and slant. Again, here we are going to discuss the first two, Hadamard and Haar. The rest we are not going to study in this course. The third one is here the basis functions depends on the statistics of the input. Let me just go back to again this. I calculated the basis function. Okay, n is 0, k is 0, it is 1. For n is 0, k is 1, it is 1. Both of them 1, it is e power j power 2, etc. Now notice here, nowhere, nowhere I have used x of n. Have I used x of n in my calculation of basis functions? No. Just carefully observe, the basis function is making use of only this term. Nowhere I use x of n. That means the signal is not considered for calculating the basis function. So whatever may be the input x of n, the basis functions will not change. Whereas there is another special category of uh, transforms where it uses some statistics of the input. That means it uses probably the mean of the input, the variance in the data, the mean of the data. Such transforms, of course, uh, there is a disadvantage because every time my signal changes, I need to calculate the basis functions. Whereas here, since it is independent of the base signal, I can just calculate the basis functions and keep it with me always. Whereas here, every time when I give you the data, you need to first calculate the basis functions and use it to transform the data. And good example is KL transform, singular value decomposition, which we are not going to discuss in this course. We will only discuss KL transform. Okay, so these are various categories of image transforms. One category uses sinusoidal basis functions, second category non-sinusoidal basis functions, and third category where basis function depends on the statistics of the input. Okay, so any doubt before we go to the math part of it? Any doubt? Can somebody respond?
No, sir.
Okay, okay. So now let us go to the mathematics. Okay, I think this part you have done under DFT, that is under DSP course. You know your transform can be represented by using matrix multiplication. Okay, so we are trying to understand this in general terms. Um, please understand what are all the, in fact, the nomenclature that we have given here. Then it will be easy for you. Whenever I use a transform, you know there is okay, a signal in the time domain, or it can be the spatial domain, and that we represent by using u of n. Okay, so u of n is the input signal, and we just start with one dimension, and we'll understand how it can be done for two dimension. And you know these are all actually finite length sequences, so let the length be capital N. So n is the length of the data, u of n is the time domain signal. Okay, now when I transform this by using some transform, it could be any of the transforms that we are going to discuss henceforth. Okay, the transformed signal is represented as v of k. So please note these notations, they are the general notations. U of n is the input signal in time domain, n is the length of the signal, and V of k is the transformed signal. And the formula is this: V of k is summation n is equal to 0 to n minus 1 a of k n u of n. Let us go back to my example of Fourier transform, then it is easy for you. Okay, I'll again write it. Let me just write it. So x of k is summation x of n e to the power of minus j 2 pi k n by capital N. Okay, x of n is 1 over n summation. Of course, I have to write what is n here. 0 to n minus 1. Here k is 0 to n minus 1. X of k e to the power of plus j 2 pi kn by n. So this is the pair. This is the DFT pair which you have already done in 5th semester. Now we will just make a small change here. That is why I told you 1 by n is a constant term. You don't need to worry. Just to keep both the forward transform formula and the reverse transform formulas look similar. Okay. What normally is done is, please note the changes that I am making. They will write 1 by root n here and another 1 by root n here. Okay. Because it's a scale factor, we are not worried much about the scale factor, because you want to convert the signal from time domain to frequency domain. I'm interested in at what frequency the signal exists. So the magnitude, I can say scale it up or scale it down by any value. So from here onwards, your DFT formula should be looked like this. Okay. Why I said it is better, because you just now compare these two signals, sorry, these two equations. There is 1 by root n here, there is 1 by root n here, so they look similar. There is a summation here, there is a summation here, they look similar, and in both the cases the sum is from 0 to n minus 1. The only change is in one case it is n, in other case it is k, but the formula is summation from 0 to n minus 1. There is x of n here, there is x of k here, so they look similar. There is an exponential term here, there is an exponential term here. The only change is here it is negative, here it is positive. Okay, so both look similar now, both of them are looking similar. This is normally the okay procedure that is followed to look at all transforms. Okay, of course in the course you would have used 1 by n here and you have calculated, but we don't need to worry because it's after all a scale factor. Okay, now according to the new notation that we are using, okay, this is your u of n. Okay, summation k going from 0 to n minus 1. This would be your u of k, sorry, v of k. This 1 by root n will be taken inside this. So a of k comma n, where a of k comma n, can anybody tell me what will be a of k comma n now? Quickly. Hello. What is a of k comma n here? Nobody is there. Let me just call Vindhya AS. Are you there? Vindhya AS. Vindhya. Vindhya AS, you are there. I don't know what is the issue, why you are not speaking. Varamahalakshmi, can you just unmute and speak?
Yes, sir.
Okay, can you tell me what is a of k comma n here? Just compare it with this equation. What would be a of k comma n? From here to here I have to go. What are the left out terms?
J into 2 pi kn by n.
It is not j, it is 1 by root n into e to the power of j 2 pi kn by capital N. So if you just plug in these values, you will get back the equation. So a of k comma n is this. I hope it is clear to all of you. So let me now go back to the equation here. So this is a general form. From here onwards, your forward transform will look like this. Now, what I have written actually is an inverse transform. So let me write the forward transform also. So V of k is equal to summation n is equal to 0 to n minus 1 u of n into, the only change now is, I think what we will do is we will just write a star here, conjugate. We will write a of kn here because normally this is the nomenclature used. That's what I think he has used here. So he has used a of kn here. So I'll call this as a star. Therefore, a of kn will be conjugate of this. Conjugate means j will become minus j. So I think it's clear. Okay. So these two are the general formulas. One, summation is from 0 to n minus 1, time domain signal, and a of kn. And inverse Fourier transform is summation is from 0 to n minus 1, Fourier coefficients, complex conjugate of the basis function. Okay, so that's exactly what I am writing here. This is actually the forward transform. Okay, so is it clear what I just want to compare it with Fourier transform because you have already learned this DFT in the class. Okay, so this is a general form. Now depending on A of kn, there is no other change in V of k and U of n and summation. The only change that happens now is depending on your basis functions. If the basis functions use sinusoids, it is DFT or DCT. If it uses maybe non-sinusoids, then it will be either Hadamard or R. And if this is calculated by using the data, it will be KL transform. Anyway, when we continue, you will understand. Okay. So this is the forward transform. I hope the point is clear. If there is any doubt, please ask me. This is the forward transform. And this is actually the inverse transform. Any doubt how I got this? Hello, please respond.
No, sir.
Okay. Now, this I think all of you have already done, but still this can be represented in the form of a matrix. Okay. How it can be done? Let me just explain it with simple example. I'll take n equal to 4. Let me use a different color. I'll take n is equal to 4. So n is equal to 4 means your small n will go from 0 to 3. Okay. N is equal to 4 means it is 4-point DFT. Let me assume that there are 4 samples in my U of n. So the formula now is V of k is equal to summation n is equal to 0 to 3 U of n A of kn. In general, don't worry about what is A of kn. We'll take it up later. Now for each value of k, let me just write V of k. So V of 0 will be equal to, let me expand this. This will be U of 0, A of 0 comma 0 plus U of 1, A of 0 comma 1 plus U of 2, A of 0 comma 2 plus U of 3, A of 0 comma 3. Hope this is not difficult. Then what is V of 1? V of 1 will be U of 0, A of 1 comma 0, U of 1, A of 1 comma 1, U of 2, A of 1 comma 2 plus U of, I think this is what you have done in DFT. Let me just expand it. So V of 2 will be U of 0, A of 2 0 plus U of 1, A of 2 1 plus U of 2, A of 2 2 plus U of 3, A of 2 3. Then the last one is V of 3. It is U of 0, A of 3 comma 0, U of 1, A of 3 comma 1, U of 2, A of 3 comma 2, and U of 3, A of 3 comma 3. Now these four matrices can be written in the, these four equations can be written in the form of a matrix multiplication, something like this. V of 0, V of 1, V of 2, V of 3. This is the result which you will obtain, and notice in your equation here, in all the equations your uh, coefficients are being multiplied with u of 0, u of 1, u of 2, u of 3. Okay, so this will be a of 0 comma 0, and this will be a of 0 comma 1, this is a of 0 comma 2, this is a of 0 comma 3. Then this will be 1 0, 1 1, 1 2, 1 3, and so on and so forth. This is a of 2 0, 2 1, 2 2, 2 3. Lastly, a of 3 0, 3 1, 3 2, 3 3. So what did we do? We are just trying to represent this forward transform equation using matrix multiplication. So this is a column vector, let me write it as V, and this is a matrix, let me just write it as A, and this is again a column vector, let me write it as U. So this is how I can write it. So here A is, so I can also write the dimension. The dimension of this is 4 cross 1, and this will be 4 cross 4, and this will be 4 cross 1. Okay, remember you have done this for DFT. I am doing it for a general case. For me it is image transform, so I'm not bothered right now whether it is Fourier transform or cosine transform or any other R or Hadamard. For me it is just a transform. So is this clear how I can write a given transform equation in the form of a matrix multiplication? Any doubt here? Please speak.
No, sir.
Okay, so uh, this is the forward transform equation, and it can be represented as V is equal to A into U, where U and V are n cross 1 column vectors and A is n cross n transformation matrix. So your A here is called transformation matrix. Now the things is, what should be the requirement of this transformation matrix? How should this transformation matrix look? For some advantages, we expect this transformation matrix A to satisfy some properties. Okay, so let us try to understand that. The transformation, okay, the transform here is said to be unitary. Okay, if the matrix A is unitary, that means if your matrix A satisfies a condition called unitary condition, then we say such a transform is unitary transform. Now the question is, what do you mean by a unitary matrix? Okay, it's very simple. Unitary matrix is one which will satisfy this condition. A into AH is equal to I. Okay, let me just write it again. So for a matrix to be unitary, for a matrix A to be unitary, to satisfy the property of unitary, it should satisfy this A into AH is equal to I. Now AH is called actually what is known as a Hermitian matrix. Okay, AH is called Hermitian, that is why it is called AH. Okay, what is Hermitian of a matrix? Hermitian of a matrix is complex conjugate transpose. Okay, that is what is written here. Complex conjugate transpose is Hermitian. Okay, so this will be Hermitian, which means that, sorry, if I think I'm using a different notation, let me just follow this only, Hermitian. Okay, so I should take the complex conjugate of the matrix, then I should transpose it. Such matrix that I get is called the Hermitian of a matrix A. Okay. Now what it is telling me is A into A Hermitian is equal to identity. Okay. All of you know identity matrix means it should be this. For example, identity matrix of dimension 4 is this. Diagonal elements are 1 and non-diagonal elements are 0. This is an identity matrix of dimension 4. Okay. So if A is a 4 cross 4 matrix, when I multiply that with its Hermitian, I should get back an identity matrix. If this condition is satisfied, such a matrix is called unitary. If such condition satisfies for my transformation matrix, such a transform is called unitary transform. Okay, so let me just repeat it. A transform is said to be unitary if the matrix A is unitary, and a matrix is said to be unitary if A into A Hermitian is an identity matrix where A Hermitian is A conjugate transpose. Okay, and what is the advantage? We will just verify it for a specific known matrix later. What is the advantage? There is an advantage. You know that if V is equal, okay, let me just go back now. So I have done a forward transformation. V is equal to AU. We have already done this. This is forward transformation. That means I have taken the signal from time domain to frequency domain. All of you know that inverse should also be there. Inverse should exist. So mathematicians say, what do they say? They say U is equal to mathematics way. Okay, this is a matrix multiplication. What is U in terms of A and V? I have already shown in the previous slide. Can somebody speak? How do I write U in terms of A and V? Mathematically, if V is equal to AU, where A is a matrix, V and U are some column vectors.
A inverse into V.
Yes, I have already shown this. A inverse into V, correct. Okay. So, if I want to do the inverse transform, I need to do this. That means I need to find the inverse of the matrix. Okay. Now, there is a catch here. Normally, the size of your U, for example, your U of n, in a real sense, if your U of n, that is your signal U of n, can go up to, in fact, it can be anything. So let me just take, for example, say U is equal to, say, some 1024 samples are there. Let us assume, okay, 1024 samples. That means your U matrix is 1024, sorry, your U matrix is 1024 cross 1. 1024 cross 1. So for this, what is the size of your A matrix? If U is 1024 cross 1, we already know here it will be 1024 cross 1024. 1024 cross 1024. That will be the size of your matrix. This is in fact, this is a very small signal I'm talking about. In real case, it will be still more. So I need to now do an inverse of a 1024 cross 1024 matrix, which is very, very difficult. Now, when it comes to image, it will be still bigger. Let me not explain it now. But this is only one dimension I'm explaining. So finding inverse of such a big matrix is difficult. If at all I want to do inverse transform, you have a challenge of performing inverse of a very big matrix. Now just carefully observe, suppose if the matrix satisfies Hermitian property, we just now wrote that A into A Hermitian is equal to identity. Okay. Now can somebody tell me, for a matrix A, if I represent A minus 1 as its inverse, what should be A into A inverse? Linear algebra. For a matrix A, if its inverse is represented as A inverse, what is A into A?
One.
It's not 1, correct? It's an identity.
Yes.
Okay. Now compare these two. Both are same. So which means that A inverse is A Hermitian. That means if the matrix satisfies unitary property, then finding A inverse is same as finding A Hermitian if it satisfies. Now just now I told A Hermitian means this is what you have to do. I have to do a complex conjugate and transpose it. Doing complex conjugate of a matrix, is it difficult? No, because you have to just replace plus j by minus j. That is, there is no big deal of doing that. Doing transpose of a matrix also there is no big deal. So if the matrix satisfies the Hermitian property, finding inverse of a matrix is very easy because I can just do Hermitian of the matrix, but that means complex conjugate it and transpose it. This is the reason why we say the matrix should satisfy, in fact the transformation matrix should satisfy the Hermitian, sorry, unitary property. Okay, so U can be found using this. Okay, U can be found by using A inverse of V, and finding A inverse is easy if it is a unitary matrix because A inverse will be same as A Hermitian. Okay, A Hermitian is A conjugate transpose. Therefore, it is preferred that the matrix transformation matrix satisfies the unitary property. Hope I have made it clear. Now the basis functions, what is the time? 8:47. We still have some time. So the basis functions here need not be always complex. Only they are complex, particularly in the case of Fourier transform. This is complex. We just now saw that, but it can be real also. So if it is real, this matrix or this values will be real values. So their conjugate will be itself. So when that is the case, uh, their conjugate is itself, so it just becomes A transpose. Okay, such transforms which will satisfy the property, okay, they are called orthogonal matrices. Okay, I repeat, a transform is said to be orthogonal if the matrix is orthogonal. And what is the meaning of orthogonal property? A into A transpose will be equal to identity. In the next class, I'll give you typical matrix examples for Hermitian and also for orthogonal matrices. Okay, so I repeat, the transform is said to be orthogonal if the matrix A is orthogonal. That means it should satisfy A into A transpose is identity. So again, the advantage is if the transform is an orthogonal transform, finding inverse is just finding transform. So if your job of finding inverse of a matrix is just doing doing just a transpose of the matrix, then your job is very simple and also in fact the time consumed will be very less. This is the advantage if the transformation matrix satisfies some properties. Okay. Um, Moving on. Now it is inverse transform. I think this I have already explained, so there is nothing much. So inverse transform can be written like this. I think we discussed this already. So yeah, it is here. So inverse transform can be, sorry, inverse transform okay, you can observe this equation. You can write the inverse transform as this. The only change is this will be A star. Okay, this will be A star complex conjugate. So that's what you see here. A star of Kn, V of k is the transform coefficients, U of n is the time domain coefficient values. So again, this can be written in terms of A conjugate transpose into V. So A conjugate transpose will actually have the basis vectors that you know. Okay, because when I represent any time domain signal in terms of the coefficient, this also I told you in the beginning. Observe this. Okay, so this is the time domain signal. These are the Fourier coefficients and these are called the basis functions. Okay, so these basis functions will sit in your transformation matrix. Observe, it will be in your conjugate transpose, that is in this matrix. So the columns of this will actually give me the basis vectors. Okay, so this is for one dimension, and maybe in the next class let us do it for two dimension. um, okay, let me just quickly, because there is some mathematics involved here, I just want you to uh, concentrate, and if there are any clarifications please let me know, because there is that some maths involved here. So what we did here is let us just try to refresh. We understood that image transforms allows to the image to shift from spatial domain to the transform domain, and one of the in fact uh, need for or requirement of this taking image transform is some operations can be made easily, can be performed easily. Good example is doing convolution. Also, by doing this, fast computation of convolution and correlation is possible, because you have some fast algorithms that can perform these type of transforms. In fact, I am already justified why Fourier transforms is fast, because you can just take the structure of these special structure of these matrices to increase the speed. The third one is data can be represented in compact form. This also I think we have understood it very well. There are three different categories of transforms based on the basis functions used. One category uses sinusoidal basis functions. These are the examples. Two of them we are going to study. Second one is the non-sinusoidal basis functions. The two of them we are going to study. Third one uses statistics of the input for the calculation of basis functions. We are going to study one. So totally five different transformations we are going to study. So all of them will use a simple structure like this. This is the forward equation. As I said, this is the time domain signal. This is the transform domain signal. This is the basis function. Now, depending on the values of k and n, basis functions change, and depending on the okay, characteristic of this basis function, it can have sinusoidal and non-sinusoidal values. And you can view this as a matrix multiplication, and the size of the matrix is n cross n, where n is the size of your image signal. And this forward transformation, if the transformation matrix satisfies some properties, then we have some advantages. One of the properties is unitary transformation. So matrix is said to be unitary if A into A Hermitian is an identity matrix. A Hermitian means complex conjugate transpose. This is a simple operation. Next class we will verify for a given matrix whether it is unitary or not. Then to find U from V, you need to do the inverse, and an advantage of a matrix being unitary is inverse can be obtained by just doing Hermitian, which is a simple operation of complex conjugate and transpose of it. Instead of complex basis functions, if I use real basis functions, then the transformation matrix can satisfy a property called orthogonality, where A is an orthogonal matrix, and we say a matrix is orthogonal if A into A transpose is identity. Now to do the inverse transform, as I said, you don't need to do the inverse of the matrix, you just do the complex conjugate transpose. This is easy. and complex conjugate. This matrix is going to represent your basis functions. V is the coefficients, U is your input data. So the columns of this will give you the basis vectors. You can just calculate it for any different values. We'll take a problem in the next class to solve this. In the next class, I am going to see whatever we have done so far. You can observe this is for one dimension. Your signal is in one dimension, but we want to treat this for two dimension. So let us just try to learn the concept of 2D transforms and then how it could be used for 2D image transforms. Okay, so I think this is where we can stop now. Before we wind up, I just want you to just okay observe this graphical user interface that was developed by uh, a group of students long back. I think this was done almost during 2010, I believe. Uh, why I want to show this to you, because whenever you are doing some MATLAB implementations, if you also use some nice graphical user interface and present it, it would be good. And in fact, I have been using this to actually teach the course every time. So what you see is I'm just running a MATLAB code. This is actually the front end of the graphical user interface. So there is a link to the next window. Now what they have done actually is they have actually given me in fact the link for so many things. Let me just explain one of them. For example, distance measures. Okay, you remember we discussed about various distances, that is the Euclidean distance, D4 distance, D8 distance. So for example, I'll just read an image and assume that I'm interested in fact this it is not actually Hyderabad, even though the name of the figure is Hyderabad. Actually this is your campus. I hope you can recognize this is actually the SIT campus. What you notice here is actually the Infinity Road that you are talking about. This is BH Road. Is this window visible to you? Are you seeing a map?
Yes, sir.
Okay, so this is actually BH Road, and this is the Infinity Road. That means from BH Road to the main building when you move. And this is actually the main building here, your administrative block here. Okay. Now suppose if I am interested in what is the distance from probably this junction point. Okay, I can click here and I can go click here. I can measure this distance and actually the distance will be displayed. So let me just go here, click and click here. Actually it is displaying, but I don't think you are able to see the result. Okay, so this is how you can measure. You can actually measure. I'm not able to move this, otherwise that display is coming in the top, bottom here. So anyway, so this is how I can use graphical user interface to measure. Let me just show you something else. For example, intensity resolution. Let me use uh, some image here, and let me represent this by using say 2 bits. 2 bits means all of you know that there will be 2 to the power of 2, that is 4 gray levels. So notice, I hope you can see the image. So there are actually 4 gray levels. There is a black gray level, there is a white gray level, there is another gray shade here, another gray shade here. The entire image is represented by 4 gray levels. Now let me just change it to say 3 bits. So you could observe that false contouring effect that you are seeing. 4 bits, the false contouring effect is decreased. Maybe 5 bits, it's further decreased. So by this I think, in fact, I can take any other image and demonstrate this. Okay, any image, you can just demonstrate this concept of false contouring like this actually. And also I think this is also an interesting thing. Now this is a color image. All of you know that color image will have different color components. So if I just ask to plot the different color components, only the blue portion, the green portion and the red portion, that is what you see. Okay, now carefully observe, this is your blue portion. In fact, if I had represented this as a gray shade, it would have been better. So I can just decompose it into RGB component and show them. So like this, actually they have provided the link for so many concepts. Like for example, this is a simple okay, scale fact, or I like just go back. Let me just demonstrate maybe rotation. So I'll take a Lena image. Suppose if I want to rotate it by an angle 45 degree, I can do it. I think it's time. So let us just wind up because we may have other classes. Um, I will discuss about this in maybe in the next class. Okay. So you can leave the class. I will not be taking attendance today. It's already time. So you can leave the class. Let us meet on Friday. Fine.